So the next sheet is you have this document, arcs and chords. So arcs and chord. And so the question you want to, there we go, my air conditioner just didn't go on. And let me shut the bathroom door, sorry. So the question is, the first question, the June 9 question, what is the distance of a point to a line, array, a segment? So that's the question. So you have a point, how do we say how far away is that point from the line? And what we saw is that we know that it's the perpendicular. We're going to say it's the perpendicular, the shortest distance. The shortest distance is considered the distance of a point to a line, a segment, array, and that's the idea. We saw there was a formula. You might look back once again. If this is x, y, well, let's call this x1, y1, and let's call the equation of this line a squared plus by, plus c equals 0. We saw that the distance was, was a x1 plus b y1 plus c divided by the square root of a squared plus b squared. This isn't showing up on the test. It's not showing up on the IB exam. It will show up on like the HL-IB exam, but we have a different method. It's not showing up on the SAT. It's not showing up on the New York State region. It's a nifty little trick to know. Anyway, so once again, arcs and chords. Once again, always imagine there's a circle. First thing, all radii are congruent. Yeah, that makes sense. Here's a circle. Here's the radii. Here's another radius. Here's another radius. They're all congruent. Number two, a point is in the interior if its distance from the center is less than the radius. Interesting. So here's a circle. Now let's call this distance r, right? So let's call this a. Here's a point B, right? And so you say, well, what's the distance, Mr. Adler? Well, you figure it out. Here's point B. And say, because AB is less than R, B is an interior point. This is a little advanced, but it's just good to know this idea to put it in your head. The radius defines the boundary. And so the word interior is like inside, but once again, because it's less than the fixed radius, we call it the interior. So let's take it to the next step. A point is in the exterior when we read from the note. A point is in the exterior if its distance from the center is greater than the radius. So we have point C. And so because AC is greater than R, C is in the interior, the exterior. That's the idea. That's a definition. So once again, you have to define the boundary and then points in relation to that, less than R, interior, greater than R, exterior. Number 4, a central angle is an angle whose vertex is the center. Number 4, this is 2 and 3. Number 4, so we have a circle, a center, this is a central angle, and this is an angle whose vertex is the center. This is a central angle. Number 5, an arc, any part of the circle. For this unit, we will want to concern ourselves with the degree measures of 360, 180. So I think we spoke about this actually in the previous unit, but the idea is if we take a circle and kind of like drop it on the floor, these parts of the circle, these are arcs. And you might be saying, and so the idea is, so you might see an arc, like, here's a circle, right? And here's here's the circle. And I drew in a right angle, or it's a quarter of the circle, and I took this off, and then so someone might say, well, what is the measurement of that arc? Please, once again, so the measurement of AB is 90 degrees. I'm not asking for the length of the arc. We're not talking circumference. That's previous. In this unit, we're just talking to it's a proportion to the original 360. So the measurement of this arc is 90 degrees. It infers that this is a quarter of the circle. I don't know anything about the radius, the diameter. I don't know. Well, the only thing I know is when you tell me this arc is 90 degrees, it's a quarter of the circle. Let's say number 6, the degree measurement of an arc is equal to the measurement of the central angle and vice versa. If this is 72 degrees, this arc AB. So if angle AOB is 72 degrees, because it's a central angle, the measurement of arc AB is equal to 72 degrees. Once again, we're not talking about the length of the arc. We're just saying this is 72. Basically, we're saying this arc is 1/5 of the circle, whose radius I don't know. Do you see that? Once again, there's a difference. I will be asking you what is the measurement, the length of this arc, but not in this unit. Let's see. Congruent circles have congruent radii. That's interesting. You never talk about that. I mean, we can't. Let's say. I mean, we can't talk about side angles. So we spent all those months on proving triangles congruent and finding all these properties. So the question is, are there congruent circles? Yeah. Congruent is a number? Yeah, what is that? Congruent circles have congruent radii. If this is a radius of 6 and this is a radius of 6, we say that these circles are congruent. Let's see, number 8. Congruent arcs have congruent degree measurements. Let's see what my diagram says. Number 8. Number 8. Congruent arcs have congruent degree measurements. So, let's say that I have 2 circles here, right? And let's say that, I said we weren't talking about, but I guess I am now. Let's say that this is AB, and let's say that this is CD. If I discover, and I go on my journey, I actually walk around, that arc AB is congruent to arc CD, then the measurement of AB is congruent to the measurement of CD. And actually the converse works also. It's very straightforward. It seems very obvious. We just want to state all these things. Number 9, congruent central angles intersect congruent arcs and vice versa. Number 9, let's take a look at that. If you have a circle and we have 2, let's see, here's a central angle, here's a central angle. Let's see, A, O, B, C, O, D. And so the idea is, it's very straightforward, but once again, it has to be said, well, we're not proving any of this stuff also. If angle AOB is equal to angle COD, then the measurement of arc AB is equal to the measurement of arc CD. Actually, and we could also say that AB is congruent to arc CD. So not only is it would be like 72 degrees, but this could be like 2 pi. And all these kind of flow into each other. If you have 2 central angles, if the arcs are congruent, then the angles are congruent. So they all mesh into each other. Let's see. Chord. Okay. Let's move on. Let's see what else I wrote. What's a chord? Number 10. A chord is a segment whose 2 points are on the circle. So AB is a chord. And then what is 11? 11 is a diameter. Let's see, CD is a diameter because it's a chord and it passes through the center. It's a chord that passes through the center. Cool. Let's see. And we know that this is 11, 12. The diameter is twice the radius. We spoke about this in another video. The diameter is generally twice the radius. Number 13, congruent. I think this is number 13 right here. Congruent central angles have congruent arcs and no. Oh, so you know what? Sorry. Number 13. Let's take it to the next step. Number 13. What am I saying with number 13? If all these angles and arcs are the same, then actually the chords are the same. And chord AB is congruent to chord CD. And they all flow into each other. So if you have this picture and you have chord AB congruent to chord DC, the arcs are congruent, the central angles are congruent. Like it all connects into each other. That's what's great about these circles. When you draw a picture of a circle, if you can get a length, if you can get the congruent length and put it on the circle, you can then get congruent angles in your diagram or whatever you need. Let's move on. 14, a diameter. This is kind of cool. Number 14, a diameter that is perpendicular to a chord. So let's see, we have a circle. Oh, let me erase that. We have a circle. We have a diameter, right? And it's perpendicular to a chord. What does that say? Couple of things. What do you think? Well, I mean, let's see. So, what do you think it does to the chord? Well, we can see it on the sheet. It bisects the chord. It bisects the chord, and it bisects the arc. What do I mean by that? Well, let's get some letters: A, O, B, C, and D. So if AB is a diameter and CD is a chord, and what else is in our hypothesis? That we're told that AB is perpendicular to CD. Then first, we're told that AB bisects this. Let's call this E. So CE is congruent to ED, and it bisects the chord up here. So I want my green pen. It bisects this chord. It bisects, and then it kind of reverses back in. So if you draw something to the midpoint, so if you draw a chord, and this actually ended up in a higher level question. If you draw a diameter through a chord's midpoint, it's perpendicular. Yeah, it's perpendicular. You have right triangles, Pythagoras theorem. So these are little tricks of the trade. It actually did show up on the IB exam. The perpendicular bisector of a chord is a diameter. Number 4, and this is just a little thing. Where's my eraser? Here it is. How are we doing for time? Okay. The perpendicular bisector of a chord, and you can actually prove this. You can prove this because you start drawing things in here. You don't know. The only thing is it's a diameter, and you're told it's perpendicular. And you're told this so. Oh, what are we told? Hold on a second. The diameter is perpendicular. So we're told these three things. Given these three things, can you prove that C is equal to ED and that CB is equal to, very easy. I mean, you draw in your radii, congruent, 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 you have right angles, hypotenuse leg, you have hypotenuse leg in there, and then if you think about it, we know that the chord is bisected, and we see here, because of CPCTC, we see that this angle is congruent to this angle, and these are central angles, which means these arcs are congruent, hence the main arc got bisected. It's a little elaborate, but like that's the idea here. And then what's the last thing we want to look at? If two chords are congruent, they are equidistant from the center. And this is a little, I mean, this is getting to like esoteric territory, but you know what? Let's just take a look at this. You have a circle, and it has a center, right? You manage to put two congruent chords in the circle, like this. So we have AB, and you have CD, and we're told that AB is congruent to CD. Then, once again, this is a little esoteric. The distance from the point, this distance, and this distance are congruent. It's kind of interesting. Maybe it serves its purpose. I don't know, but these are just really interesting things about the circles and arcs and chords. And that's basically it. Is that it? Want to talk about? Yeah. And you know what? You can prove this easily by just creating all these triangles. You know, congruent, 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 they're all congruent. We're told it's because it's radii, these are congruent. An isosceles triangle, the altitude is congruent. We learned all this stuff. So that's how we can prove that if you have a circle, you can construct a circle, and you draw two congruent chords in, the distances are equal. That's another way to find equal distances. That's it.